Hello and welcome to this technical presentation of thermostatic mixing valves for domestic hot water systems in residential applications. My name is Max Rohr. I'm the Education and Industry Engagement Manager for Caleffi North America. I'll be walking you through the slides today. So I'm going to turn the camera off so you can see the slides a little bit better. Okay, so to start with, generally mixing valves are thermostatic style mixing valves for residential applications, but there are some electronic options too. You'd probably see those in more of a commercial building, a larger building. Often you'll see TMV for thermostatic mixing valve and other literature as an abbreviation. So why do we use a mixing valve? First, to supply consistent hot water to all the plumbing fixtures, kind of regardless of what's happening in the mechanical room with your water heater, if it's a consistent temperature all day, every day, or if there are some fluctuations like you would see in any water heater, whether it's electric or gas or something. When it turns on, it may heat the water a little bit warmer than your set point by a couple degrees and then fall a few below before it refires. And that's normal. So we use mixing valves to kind of sort that out, to smooth that out a little bit. We use them to protect occupants from high temperatures. So again, whatever happens in the mechanical room, we don't want water to leave the mechanical room and hit a faucet somewhere where you could scald somebody. Just as plumbing professionals, that's what we're trying to avoid. Another thing that they can be used for is to add capacity to a water heater. So you can store the water warmer and build some more capacity into that water heater without purchasing a larger model, as an example, just by storing it a little bit warmer. Bigger picture, what we're trying to do is enable load shifting at the utility level and keep our utility bills low by staying off-peak electrical. So in a sense, I'll go into this in a little bit more detail, but what we're trying to do is boost that battery, that thermal battery that we have in the mechanical room, and then to coast to some extent through the periods where we don't want to use electricity because it's more expensive and it's may cause brownouts if everybody just had their water heater on at the same time in extreme cases. So that's one way that we give customers exactly what they want, which is hot water during demand response time of use periods without noticing anything, without having the customer pay more than they need to because they're on the peak rates, and also helping utility companies as well to maximize the benefits of renewable energy and not have to bring on peaker plants and things like that to make the mix of energy less clean. So those are some of the main goals, and how we can help with thermostatic mixing valves is generally by just smoothing out that delivery. So there are two different styles generally of mixing valves in the thermostatic mixing valve category. So a point of use distribution mixing valve is going to be an ASSE 1017 listed valve. This is generally located near the water heater, serving the hot water fixtures for the whole building. Point of distribution. A 1070 valve, like in the bottom right corner, would be something used in generally a commercial setting, like a hospital or school, where you put one of these mixing valves or one next to a couple faucets, one per faucet, like you'd see in an airport as well, to limit the temperature at the sink or at a bathtub. So the 1070 valves on the bottom there are used for scald protection. They will actually stop flow when they exceed the set point. The valves on the top right there, point of distribution, is just smoothing out what's leaving the mechanical room within reason, but it does not close per the ASSE listing the hot port or the mix port completely to stop the flow of hot water out into the building. I'll cover that in a little bit more detail in some of the valve designs as well. But the reason that we do that is even 140-degree water for 10 seconds, that's enough to give you a partial burn. And anything warmer than that, if we get into some of the load shifting scenarios where we're storing warmer water, we really can't have that hit the fixtures in a house where we risk scalding somebody pretty quickly. And that's what we want to avoid at all costs. So another reason that we would use this thermostatic mixing valve is to increase capacity without buying a bigger tank. So let's look at this example and say that you live in Atlanta, Georgia. So you're in this, this orange 62-degree incoming water band here. So if you have a 60-gallon water heater stored at a baseline of 120 degrees Fahrenheit, you could increase the temperature, the set point of that water heater, to 130 degree Fahrenheit, and you would add 17% capacity there. So if you stored it even warmer at 140 degrees, capacity increases to 34% above that. So essentially, you're turning a 60-gallon water heater into an 80-gallon tank without letting 180 degrees Fahrenheit leave the mechanical room. That's why you use the point of distribution mixing valve. And that next slide will kind of go through the explanation there. So these are a couple simple piping diagrams here. Just a simple valve with or without a domestic water recirc connection coming into the building if it's a larger house. But pretty simple components to allow you to gain some pretty significant capacity there. There are some cases too that just a bigger tank wouldn't fit in the mechanical room. So a 60-gallon water heater stored warmer could be a good solution there. Okay, so this chart is a little complex, so I'm just going to kind of walk through it slowly here. So the y-axis is the cost per kilowatt hour of the electricity in this case. The x-axis are going to be the 24 hours of the day. So what you see here is a visual of water heater energy use with and without load shifting. So to start with, I'll do our black line here. So this would be a water heater's electrical consumption without load shifting. So if you have an electric water heater and you just plug it in and use it as normal, here are the times that you may use more electricity. And then the problem is when you are on this larger kind of bar graph that shoots up right here, that's going to be higher electrical rates. If we just have an electric water heater plugged into the breaker and it goes all the way through the day, it's going to be using energy when it costs the most and really when it's least helpful to the utility company. We want to kind of drop out on anything that's unnecessary there. So in a scenario where we have a heat pump water heater and we're going to go with a load shifting scenario, what we might do is charge that tank up a little bit warmer. So we're going to use more electricity to boost that tank storage temperature in the morning when the rates are still low. And then we'll kind of just let it coast. And I'll go through kind of the examples of how this doesn't impact the homeowner at all. But we've overcharged it, so we've gained some capacity there. And then we're going to try and keep that water heater off for a good portion of the peak time. So best case scenario, we don't even fire it up while the rates are higher. So this red scenario, we let it drop off for those evening hours, and then we start to charge it up again after we're off peak again. So the way that this works is that you don't turn the water heater off, you're just limiting the demand. So again, the key here is to make sure that the homeowner doesn't even notice that this is happening. We're just charging the water heater up a little bit when the rates are low, and then we're trying to minimize the amount of cycles during the peak times in order to best benefit from that time of use rate avoidance, but again, without making a scenario where you're going to take a cold shower in the afternoon or something like that. We don't want that for the homeowners. Okay, so while the tank temperature may change during the day, when done properly, the occupants may wash their hands, take a shower at any time throughout the day and not notice any difference in the water temperature. So it's not safe to send 140 degree Fahrenheit water out to the building, as we mentioned before. So even if the water heater can produce it, what we're going to do is limit the outlet temperature in this case to, as an example, 110 degrees leaving the mechanical room. So we're staying well below that, higher risk of scalding there. Even though the tank set point may be higher, you may have charged that up to 140 degrees. You kind of let it coast a little bit during the evening hours and during the day, and then you charge it back up. So all of this is happening in the background. The only thing that the homeowner sees, regardless of what minute in the day they take a shower, is a consistent delivery. That's what we're looking to do with a thermostatic mixing valve paired with a heat pump water heater. So one thing to note for installers when you're putting these systems together is all mixing valves are going to have a minimum temperature difference between the hot water inlet and the mixed water outlet. So in the case that you're storing your water heater up to 138 degrees, with an 18 degree Fahrenheit number there, that means you won't get more than 120 degree Fahrenheit water out. So if you store your tank at 138, that does not mean you're going to mix to 1 37 and send that out to the building. You have to subtract that minimum temperature difference between hot and mixed outlet, and that's going to give you a realistic number of the delivery. So what can happen is if you store the tank to 120 degrees and then take an additional 18-degree penalty there, that may be cooler than what the homeowner has had in the past with a gas or an electric water heater, and they may say, well, this water heater does not produce warm enough water for my liking, and they're going to be upset about that. So that number, that minimum temperature difference, is going to help you out in your design to know where you need to store that tank. Okay, so let's look at a couple different residential project examples. This is probably a realistic one. No engineer drawings can be found. You don't know what the minimum or maximum GPM demand is. We'll say that this is an existing building, 2 shower tub combos, 3 sinks, 3 toilets, washing machine, dishwasher. So the traditional way to do this is to use calculations from the 1940s. Dr. Roy B. Hunter put together the set of calculations that we refer to now as the Hunter's curves. So these calculations were built in a time that a toilet flush might be more than 5 gallons of water. These fixtures aren't really part of the landscape anymore in modern plumbing systems. So anything that's up to code in the last 20 years is going to be much lower flow requirements for all these different fixtures. So in some cases, engineers will have their own modified version of the Hunter's curve to come back down to more realistic numbers for the amount of gallons per minute that these fixtures will use. But unfortunately, the Hunter's curve, just as it existed in 1940, is what most jurisdictions accept to do flow calculations. But what we found more recently is it is widely oversized, and that kind of hurts the industry in a few different ways and leads to some energy waste and oversizing of components and things like that. So a modified Hunter's curve is fine as long as whoever's doing the calculation is kind of adjusting it for the fixtures that are on the market with low flow fixtures that we would see today at a plumbing wholesale house. So another option, this is something that you're going to have to check with your authority having jurisdiction to see if this is allowed, but IAPMO has put together a water demand calculator. This is a free download that you can see the URL right there. Maybe just for a sanity check, for kind of a reference to see, well, what does the water demand calculator say I need? And the number you're looking for is your peak demand flow in gallons per minute there. And it may be drastically less than what the Hunter's curve would be, and that's a good thing. So that's going to be more realistic to the fixtures that we see on the market today, and is something that could really help with the adoption of any type of water heater in the future to minimize installed cost and not affect the performance of the device at all. You're just not so wildly oversized. So what you need to look for here is, again, check with your authority having jurisdiction and see if it's allowed in the Uniform Plumbing Code Appendix M. Some places, like the entire state of Wisconsin now, allows this, but it may be city by city in other places. So in our project example number 1, we go through the calculation here. We put in all of our fixtures for a single family residence, and we get 11 GPM. So now we're going to pull up a thermostatic mixing valve hydraulic characteristic chart, and let's figure out which valve that we need for this system. So if we look at our maximum flow rate, got our 11 GPM there. And what that's showing is that 11 GPM, we're going to have a delta P, a change in pressure across that valve of 10 PSI, just under that number. And that's good. Anything above that number, and you'll start to notice that at the fixture. So if you went up to a 50 PSI drop across that mixing valve because you were shooting for a higher flow rate up to 20, you would have a very kind of sluggish flow out of a shower, something that the homeowners would definitely notice. So you want to stay below that 10 PSI is a general recommendation. Some engineers will say 7.5 or have their own number, but that's a good place to shoot for. So in that case, we are going to select a 3.5 CV valve, this black line right here. If we went with the smaller CV valve body, it would be too much of a pressure drop. So let's go with that 3.5 CV valve. Now let's look at a second example. So in this case, let's say it's an engineered design, it's new construction. We know from the engineer based on this building that it's a 1.3 GPM minimum and a 5.5 GPM maximum. They've gone through all the calculations, they've figured out what that number is. So that's something that we can take those numbers and just go right to the selection chart. We don't have to do any of the homework ourselves. So in this case, if our maximum is a 5.5 GPM, we can go with the smaller valve. So this is something that's going to save some cost on the project because it's going to be less brass generally. The valve body will be smaller than a larger CV valve and is going to be the better performance curve for the product that we're looking for. So we'll go with the 2.0 CV valve in this case. And then for our minimum flow rate, we're well covered there too. So that goes down to the low end, the 1.3 GPM there. You want to make sure that your curve will cover the low end as well. And to go into a little bit more detail with that, the reason that you want to pay attention to the minimum flow requirement, and this is something that you'll look at the valve specs and see what the different minimum and maximum performance characteristics are. So if we went with that smaller valve body, in this case, the minimum flow rate is a 0.5 GPM, but the 1-inch valve body a little bit bigger would be a 1 GPM. Now, some thermostatic mixing valves will have the same size tail pieces. So this 1-inch valve with a larger CV and a larger valve body, the minimum GPM is 4.4. So that's going to be too big for the low end of that project too that we talked about. So if the minimum flow rate was 1.3 GPM, but this valve, even though it's still a 1-inch valve, is up to 4.4, it's going to be too big. In bigger homes, the recirc pump can make up for the minimum flow. So it's really just to make sure there's enough turbulence going through the body of these thermostatic mixing valves in order for the sensor to react and have stable performance. If you're below that minimum set point, it can hunt. So it can shoot a little high and shoot a little low and kind of oscillate back and forth, which you would notice in a shower or something like that. And it's not something that we want. So again, both have 1-inch connections. Connection size is not enough to size a mixing valve. You need to look at the chart a little bit deeper and make sure you've got the right product. Okay, so to look at the CV a little bit more too, so some of these different mixing valves, these are the same two from the last page. This valve, the smaller one, has a CV of 3. It's going to be a lot less expensive. This valve has a CV of 7, but it's also going to cover a much larger flow rate without too much pressure drop. So I'll kind of walk through this chart on the bottom here. So if we're looking to find the CV of a valve, we don't know it, it's something that's existing, we can take some pressure gauges upstream and downstream of the valve, find what the pressure drop is across it, and then if we know what the flow is in GPM, that's our easy CV. So in this case, it's a 3. So if you know any two variables, you can calculate for the third. If we know that there is a 20 PSI drop across the valve and we know that that is a 3 CV valve, we can figure out that we have 13.42 GPM across the valve. Now, if we want to find the pressure drop, we know that we have a CV of 7 with the valve. We'll say we're using this larger one in this example, and we've got a flow of 13.42 GPM. We can calculate that the delta P across that valve is going to be 3.68. So look at the difference between a 3 CV valve is going to have a 20 PSI drop across it, which is higher than what we had said was a good number with that 10 PSI drop. With the larger CV valve of 7, it's only 3.68. So it's a much better valve for that flow rate of 13.42 GPM. The larger valve is going to better handle those flow rates without affecting the fixtures. Okay, so in the bigger context of electrification, the first step here is that we're changing gas water heaters out for electric heat pump water heaters in existing homes. That's kind of what we're trying to do. But that's setting us up for something that's a little bit more important at the utility level to be able to charge up the water heater like it's a big electric battery. It's just as a big thermal battery down in your basement. And it's going to help us not use as much electricity on peak. So we store it warmer, we coast through those peak periods. One of the things to keep a note is plan for ongoing maintenance with these systems. So the warmer we store hot water, the faster scale develops on the components. So if you stored water at 195 degrees Fahrenheit, that would be a bad idea for a lot of different reasons, and it would be expensive to do that, and potentially dangerous. You would also scale all of those components, the hot water components in your system faster. Your thermostatic mixing valves, the faucets, it pulls the minerals out of solution at the higher temperatures, and they're going to stick to the inside of the components like glue. So know that if you store at higher temperatures, you do need to pay attention, and at least once every year to start with, see how fast those components are scaling up, and know that they need to be part of a service plan to make sure that you're descaling, or at least planning for replacement of some of those fixtures, maybe a number of months or years faster than if you stored water at 120 degrees year round. So we still get the benefit of all the things that we've talked about. You just have to pay attention to it. It is a machine, heat pump water heater that requires service. So another thing that we want to do is avoid that all electric resistant control mode for the best coefficient of performance result. So talk to the heat pump water heater manufacturers, whoever is making the machine that you're going to buy and install in a home. See what temperatures are realistic. They may say, yeah, if you want to store at 150 degrees Fahrenheit, you're going to be in all electric all the time, and you're really going to hurt the performance of that water heater. That's something to note, to say, okay, well, why don't we target 135 instead and maximize the amount of time in a day that it's in heat pump only mode, because anytime that we go to straight electric, the COP goes to 1. So you may have a much higher number if you're using the heat pump. If you're just using electric resistance, then you're going to get kind of the worst performance for your kilowatt hour dollar that you can get. So you want to avoid that unless it's just to recover a tank that was bogged pretty quickly, but you still have a dishwasher to run or something like that. So utilize point of distribution and point of use mixing valves to protect occupants. And then again, set the expectation that you do need to service this equipment for optimal performance. One other tricky topic when you're considering a thermostatic mixing valve or an electronic mixing valve as well, to look to prevent is a scenario called recirc creep. So this is a scenario where generally at 3 in the morning, when there isn't much demand on a system and you have a recirculation system, pump in your house to circulate the hot water to all the different corners of the building. If nobody's using any water, if you don't have a mixing valve that will close the hot port 100%, that's just a criteria to look for in a valve for selection, what can happen is the water coming back to the cold port can start to increase in temperature because nobody's using it in the recirc line if the recirc line ties in on the cold side. And then essentially you're mixing hot water with hot water from the water heater, and that can exceed your set point. It's kind of a ghost thing to troubleshoot because it's going to happen at 3 in the morning. The first person to turn on the faucet early in the morning might get just a quick blast of really hot water, but then it will go back to normal as soon as you have increased demand on the building, and it becomes a very hard thing to troubleshoot. So just valve selection with that 100% hot close off feature is something that's really important. You can also balance it with a globe valve to have it split and go back to the water heater as well. So you're just matching the heat loss of the recirc line basically and kind of throttling it back into the tank. Much harder to troubleshoot. So still a possibility. That's something that's been a trick for many years, but just closing that hot port is an easier way to fix that. Now, another thing to look at in residential cases, there isn't as much hot water balancing, but it is something that manual, automatic, or thermal balancing valves can help with a large building or multifamily building. Make sure that the hot water goes to all different risers and laterals in the building evenly, and you're basically making sure that the hottest water doesn't just follow the path of least resistance back to the mechanical room, because that can be a waste of water. You've got long wait times, and it's a waste of energy because you're circulating water to places that are warm and don't need any more hot water. So this is something to check with your heat pump manufacturer to see if they have specific recommendations for recirc, but know that there is kind of a give and take here. So No recirc is in some cases better because you're not taking energy that's stored in that warm tank and dissipating it all over the building. But it does mean in a larger building, if you're 50 feet or more from the hot water heater, that you may have longer wait times, and you may actually be outside of the code as well. Usually 50 feet from the water heater is something that's a maximum number of feet without having to boost it with an electric point of use water heater or something like that. So you really don't want uncontrolled, uninsulated hot water recirc loops in any scenario. That's something that is a waste. So what we want to do with balancing valves and mixing valves and all the different pieces that you put into a modern plumbing system is to make sure that that's really the laziest recirc that it could be. And so we just want to move, ounces of water per hour through the house in order to keep the wait times low so we're not wasting water, but also to just use the smallest amount of electrical energy to accomplish that task. And then thermal balancing valves are a great way to go in that case too, because they're a temperature modulation, not just a flow rate. So that helps kind of dynamically adapt to the building as the temperature changes in the recirc loops. Okay, for more resources on these topics, Caleffi offers these free trade journals. You can sign up for hard copies or just download the PDF. On the website, we have an interactive hydronics version as well with supplemental videos and things like that. So all three of these issues here, 11, 21, and 22, are on the topic, just in a lot more detail, a lot more ways to kind of calculate the different scenarios for DHW delivery systems that are going to be a very modern, great way to go for your occupants. Another series is a webinar series we call Coffee with Caleffi. These are live webinars every month, archived on YouTube. You can go in and look for specific topics there and go into a little bit more detail as well. You can always visit caleffi.us for more information on specific products and applications. We're happy to help out there. So thank you for your time, and hopefully this has been helpful to design the best case scenario heat pump water heater system for your customers. Thank you.